Alright, welcome to this lesson on how do we investigate proofs and prove triangles congruent. So the first thing is that we're gonna go over a couple of properties, okay? So as to prepare for our geometric proofs. So what is a proof? A proof, well, is a valid argument that establishes the truth, okay? The truth of a statement. So that's what we're going to be doing. So the first property that we're going to be looking at is the reflexive property. Okay? Reflexive property. Now, what does that say? It's a silly property. It says that you are equal to you. That I am equal to me. That TV is equal to itself. So in other words, the reflexive property says that a quantity is congruent or equal to itself. Alright? So let's see what's up with that. Reflexive property, A equals to A. Now why do I need this property? Well, imagine if you had a triangle like this. Something like, oh my god, let's pretend, oh my god, let's pretend this is an equilateral triangle. Okay, and now there is this altitude right here. So let me label this triangle A, B, and C. Alright, you should be writing this on loose leaf paper, just in case. Alright, let me call this point D. Cool then. So, notice something. If I want to prove that this side is in reality two sides. What do you mean? Well, think of it this way. BD, side BD, is a side common to two triangles. This side belongs to this triangle ABD, but it also belongs to this triangle CBD. Make sense? So it's actually two sides in one. Alright, so cool. Oh, I caught you, okay. So basically this is the reflexive property. So copy it and then we move on to the next property. By the way, let me see. You could say a side is equal to itself or an angle is equal to itself. Just in case. Is anything equal to itself? Alright, let's move on. The next one is the symmetric property. Okay, so symmetric property. Alright, symmetric property. And what does it say? Nothing more than, let's say you have a segment, let's call it LM, in another segment, calling it, I don't know, NP. Okay, so you have these two segments. Let's pretend that they both are congruent, meaning having the same length. So I could say that LM is congruent to NP. Guess what? The symmetric property says that if you go from one place to another, then you can go from another place to this place. What I mean is this. LM is congruent to NP, therefore NP is congruent to LM. Or if you want to put it in different terms, if A is equal to B, then B must be equal to A. If you are 20 years old and I am 20 years old, then you are equal to me and I am equal to you. That's all it says. Nice. Okay, that is for the symmetric property. The next property is the transitive property. Transitive property. the transitive property. You know what? Let me zoom in on this one. Okay, better. So basically, this is what it says. And let's write it down. Transitive property. I'm going to give it to you in symbols right now, and then I'm going to explain to you what it means. A equals to B. B equals to C. Therefore, A is equal to C. What the hell? Listen to me. If I am 20 years old, right? B is 20 years old, Becker. Then Carlos or whatever, C or B, no. Let's use A first. So I use A. So Anna is 20 years old. Becker is 20 years old. Carlos is 20 years old. Therefore, Anna has the same age or is the same age as Carlos. Make sense? So, if one quantity is equal to another and that other quantity is equal to a third quantity, but they're all equal, then the first quantity should be equal to the third quantity. That is what the transitive property says. So if A is equal to B and B is equal to C, then A is equal to C. We could use numbers. If A is 3 units, B is 3 units, and C is 3 units, then I can say that A is equal to C. Okay? Can I see that? Yeah, barely. Okay. Nice. From home. Okay. What else? Do we have any more properties? Yes. And by the way, these are properties of, you could call it congruency or equality. Okay? Because you could prove something congruent or something equal, which they kind of like equivalent. Alright. So, let's have an example right here. The example is right here, by the way. You know what? Let us just do it right this way. Okay. I think so. No. Let's write it over here. Come on. I'm using the board right here. Okay. So, it says, example. Segment AB is congruent to segment BC. And segment BC is congruent to segment CD. This little bar on top denotes that they are segments. Alright. So given segment AB congruent to BC. Oh wait, I said that already. Sorry, my bad. Okay, I want to prove. What am I supposed to prove? They want me to prove that the length of AB is equal to the length of CD. Notice, if he has a bar on top, means segment. Okay? Segments are congruent, not equal. Or you could say equal. Now this one, it doesn't have the bar on top. It's like the measure. Okay? So AB is equal to CD. How am I going to prove this? Easy. Now that we are actually exploring this, we're going to explore the proofs. In a proof, you divide it into 2 columns. One column are the statements, okay? And in the other column, you write the reasons. So, for example, the first statement that you will always write is the given. What was the given? Well, the given was that AB is congruent to BC. So my reason for that is, well, it was hello, it was given to me, hello. Okay. Within the same statement, or if you want to put it as a different statement, they also said that BC segment BC was congruent to segment CD. Okay, and now what? Well, that was my second statement, and guess what? The reason for that is that it was given to me. Alright, so we need to prove that AB, the length of AB is equal to the length of CD. Well, watch this. If AB is congruent to BC and BC is congruent to CD, I can conclude that segment AB is congruent to segment CD because they're all equal. Okay, so that's exactly what I'm going to do. So my third statement, okay, can I see my third statement? Yes, okay. So then I can say that AB, okay, this one is congruent to this one. So AB, segment AB, is congruent to segment CD. Okay? Now, what is the reason behind this conclusion? Well, I just explained to you what the transitive property does. You have three quantities, and if they are equal, then the first quantity can be equal to the third quantity. Oh, nice, Becker. So, my reason is that it's because of the transitive property of congruency. All right, I'm gonna zoom out a little bit so you could actually see what I'm writing. Okay. Now, if two quantities are congruent, and this is forever, ever, ever of always of the ever, ever, evers, okay? If two quantities are congruent, they are equal in length, measure, degree measure, whatever you want to call it, okay? Yeah, I just woke up. Alright, so if these are congruent, then segment AB, okay, the length of AB, you see, I'm not putting any bars in here, but if I wanted to, I could actually. So AB is equal to length with CD. Okay? Now, I gotta write the reason right here. The reason behind this is that if two segments are congruent, we just explained, I mean, you could write an essay if you want to. You don't have to do like the 2-column proof, but you could just say, if two quantities are congruent, then they are equal in length. So that is the reason, okay? Congruent segments. Okay, I'm gonna have to zoom out a little more. Let me see, can you see it? Barely. Okay, congruent segments, okay, are segments that have, okay, I'm not gonna write it because you won't be able to see it, that have the same length. All right? Yes? Good. They have the same length. And basically this is how you conduct a proof. Alright. So let's continue with our next property. Okay? Hold on. Alright, so now let's take a look at the the substitution postulate. Substitution. Listen. Okay, you don't need to see my face. You just need to see this. No. Alright, so basically here, if x is equal to y, and y is 8, what do you think the value of x is? If x is equal to y, and y is 8, then I can conclude that x is also 8. If y is 8, then x is 8, and vice versa. That is called substitution. Okay, you can substitute equal quantities with equals. So let's look at this example, okay? Given the length of segment CE, the measure, you see we're using the equal sign. So the length of segment CE equals to 2 times the length of CD. Then, and CD is equal to DE. Okay. They want me to prove that segment CE is equal to 2 times the length of DE. In other words, if let's see if I can come up with an example. If 6 is 2 times 3, right? And CD is equal to DE. Hold on a second. Oh, I see. We don't have I can make a diagram if you want to. But watch this. Let's conduct the proof first. Segment CE is 2 times CD. Okay. Now, what is my reason? Well, it was given to me. Second statement. CD is equal to DE, right here. What is the reason? It was given to me. Okay then. So, let's see if I can come up with a little diagram to show. I really don't know how to do the diagram, but hey, listen, that's what we're here for. So let's say I have a segment. Okay? Now, I guess the whole thing, okay, I have C, D, and E. So I'm going to assume that this is C, right? Let me see if I can do this. C, okay, CE. CE is twice the length of CD. So CE is twice the length of CD. Okay? So now I can see what's going on. CD is equal to DE. So now let me actually do the following. CD is equal to the measure of DE. Ah, I did it. Now, can you see that? That's the thing. Oh, yes, you can. Okay. So, this was given to me. So, this segment right here is equal to this segment right here. Cool. Now, CE. You see that? CE is twice as long as CD. Now, it does make sense. This segment right here, CE, is 2 times this segment CD. And how do I know that? Because these two segments are congruent. So, let's say this is X, right? And this is, or if this is X, this has to be X as well, because they have the same length. If this is 3, this gotta be 3. So, when I actually get them together, 3 plus 3 is 6. That's 2 times the length. I hope I'm making sense. Okay, so now, guess what? CE is 2 times CD. But guess what? CE is also 2 times DE. Alright? So that is why we can use the substitution postulate. Okay? Equal quantities may be substituted by equal quantities or with equal quantities. Got it? Alright then. So now what can I conclude? Let me just leave it here. What can I conclude? Knowing that CD is equal to DE. So then if it's twice CD, then guess what? CE may also be twice DE. In other words, all I did is knowing that these quantities are equal, and that this is 2 times this little length, then I can substitute equal quantities with equals. So instead of CD, I could just write DE over here. And that is my conclusion right here. Okay then, so my reason behind that would be what? Well, substitution, okay, substitution postulate. And if you want to be more specific, you could say that, okay, you could say that equal quantities may be, okay, replaced or substituted by equals. That's what it says. Okay, so we got that. Guess what? This is the hard one. So now let us go on to the easy part. First of all, let us recap on the properties that we just learned. Okay, so we learned about the reflexive property. Reflexive property. I am equal to me. You are equal to you. A is equal to A. B is equal to B. And it's usually used when you want to share, okay, when you want to share sides of a triangle. Like this side is a side of this little triangle, and it's also a side of this other triangle. Okay? So that's one. Then, what else did we use? We use the symmetric property. So, symmetric property. The other one that we used was the transitive property. Learn how to spell it, Becca? Transitive property. Okay. Then we learn about the substitution postulate. Now listen to me. There's a difference between a theorem and a postulate. A theorem is something that can be proven. Okay? You need to prove that. But a postulate is something that is assumed to be truth without any proof. Like for example, a line is a set of infinite many points. But then again, I mean, that's what we assume. But what is a point? A point is nothing more than is represented by a dot, is invisible, it has no length, no thickness. But then again, how can we form a line that we can actually see, but with points that have properties of invisibility, because we cannot see it, therefore because they don't have any dimensions. All right, anyway, so these are the properties. There is also something called the addition postulate, the subtraction postulate, but you know what, we're going to just use our deductive reasoning, okay, to come up with the proofs. All right, so let me erase this, because now we are going to prove triangles congruent. Now, there are different ways of proving triangles congruent. Okay, this is on your handout, by the way. So let's say you have two triangles. Okay, they have the exact same measure, they have the exact same angles, they have everything. That's why they are congruent. So let's call this A, let's call this B, let's call this C, let's call this D, let's call this E, and let's call this F. So different ways of proving triangles congruent. let's pretend that they are actually congruent in every aspect. So I'm going to say that side AB is congruent to side DE. Make sense? Yes. I'm also going to say that side AC is congruent to side DF. I will also say that angle A is congruent to angle D. I'm just saying this. But now, funny thing is that I just proved this triangle is congruent. How? Easy. If you have a side, right? Then, I'm sorry, if you have two sides, but you have an angle in between, then you have proven your triangle is congruent by side, angle, side. Got it? Okay then. But then let's say that you don't have that. Let's say that you have something different. Let's say that instead of the angle, you actually have three sides congruent. All three sides of this triangle are congruent to all three sides of this triangle. Therefore, that's another way of proving triangles congruent. And you have proved them congruent by side, side, side. Nice. Okay then. Now, let us go on to a different way of proving triangles congruent. Okay? Let's say that you have, wow, I got a lot of stuff here. Let's say you have an angle here. Angle A congruent to angle D. You have side AC congruent to side DF. Then you have angle C congruent to angle F. You have just proven triangles congruent by what? Take a wild guess. Angle, side, angle. So we got sas, we got s, and we got asa. All right then. Is there another way? Yes, there are other ways of proving triangles congruent. Let me erase this. Okay, so now let's say that you have this angle is congruent to this angle, that this angle is congruent to this angle. Remember something, if you have two angles of a triangle, okay, and you have another two angles of another triangle, if this is, let's say 40-40, then this is 100, because in a triangle we have 180 degrees, right? If this is 40-40, this has to be 100 degrees, okay? Making our triangles kind of congruent. But this could be longer or larger than this, and they could still have the same degree measure. So I need a little more. Oh well, sure. Let's say this side is congruent to this side right here. That's it. That is enough to prove that the two triangles are congruent by what? By angle, angle, side. Okay? And how do I read this? As. Okay? As. Good. As. How do you read it? As. Good. Okay. So now, another way of proving triangles congruent. Let's see if we have any more ways of proving triangles congruent. Yes. I'm going to show you right now something that you shouldn't use. Okay? For example, you cannot prove triangles congruent by angle, angle, angle. Why? They might have the same degree measure, but that doesn't mean that they have to have the same length measure, the same side measure, okay? So, right here, you cannot, ugly A. You cannot, okay, you cannot prove triangles congruent by angle, 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 okay? Another thing that you cannot prove triangles congruent with is the following. Let's say you have just the angles, okay? You have one angle right there. So, angle, and then you have a side, and then you have another side. Remember, this is not side, angle, side. No, this is as. You cannot prove triangles congruent using as, okay? You could use as right here, but you cannot use as. Oh, I think I'm, okay. So, angle, 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 and angle, side, side cannot be used, okay? As. You cannot do that. Sorry. And yes, definitely you cannot. Okay, so this concludes our part on proving triangles congruent. Alright? So, now, we are going to also use do one last problem just to show you. Alright, so I'm going to draw two triangles, always two triangles, okay? And I want you to tell me how are they congruent. So, how are they congruent? They are congruent, exactly, they are congruent by side, angle, side. Okay, so let's do another one. Alright, how are these angles congruent? They cannot be proven congruent. So if you thought like that, you're right. They cannot be proven congruent. Angle, angle, angle cannot be a method of proving triangles congruent. What about now? Okay? Can I prove triangles congruent like that? What do you want? Sit. Fine. You want to be on camera? Fine. Here. Okay, yeah. You're on camera now? Okay, goodbye. Get lost. Okay. So, what is this? They cannot be proven congruent through as. Remember that. Okay. Let's see now. Okay, watch this. That, right? Let's say I have this angle congruent to this angle, okay? Because that's basically what it is. This is this part right here, okay? And let's see now. This side, okay, congruent to this side right here. Alright, I'm gonna say that this is the midpoint, whatever. So, hey, stop. Alright, now these two triangles are congruent by what? Good thing you asked, because right now I'm gonna show you something. Sometimes even if it's not given to you, well, it is given to you invisibly. Vertical angles are formed by two intersecting lines. And vertical angles are congruent. So that means that this angle right here is congruent to this angle over here. I don't need to see it in order to actually realize that. So now I can say that these two triangles are congruent by angle, side, angle, side, angle, angle, side, angle. Asa. Say asa. Now say asa.
Asa.
There you go. Okay, so that's basically it. Okay, let's conduct our first proof. Okay, so we have quadrilateral. Look at the proof. It says given quadrilateral ABCD. Alright, segment AD, that's this segment right here, is congruent to segment AB. Okay, segment AD is congruent to segment AB. Alright, cool then. Angle 1 is congruent to angle 2. So angle 1 is congruent to angle 2. Alright, cool then. They want me to prove that CD is congruent to CB. They want me to conclude, okay, to prove that CD, this side, is congruent to CB. That this is congruent to this one. Alright, so this is how we do it. From now on, we're going to be doing proofs, and usually it involves proving triangles congruent. So at plain sight, I can see that this triangle right here, ABC, is congruent to DCA or ACD, whatever you want to call it. Funny thing is that I cannot just assume that. I have to actually prove it. So I will. And watch this. When we conduct a proof, on one column we write something called the statements. On the other one we write reasons. Okay? And you have to number them so you know which statement goes with which reason. Okay? So I am going to label this 1. AD is congruent to AB and angle 1 is congruent to angle 2. Guess what? They were given to me right here. So I write given. You don't have to write given to me. No. Now, for our second statement, I was about to do it before, but now let's do it together. I know I can prove triangles congruent by angle, side, angle, by side, 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 by angle, angle, side, by what else? Angle, side, angle, side, angle, side. Okay. Remember that you cannot prove triangles congruent by as or by angle, angle, angle. That's the only thing that you have to remember. So I got an angle, I got a side. Can I say that this is congruent to this one? Nah. That's what I'm supposed to prove. But how? Easy. Look. AC. You see this AC? Guess what? AC is congruent to itself. AC is congruent to itself. Yes. What is the reason? By which property? That is what I want to know. So, would you be able to tell me under what property one is congruent to the other? Right. Under the reflexive property, they are congruent. So, that's what I write. Reflexive property. Okay, a quantity is congruent to itself. I mean, you could write it if you want to, but I really don't. Oh my God. Let me see what's going on here. Okay, we're good then. Alright, so a quantity a quantity is congruent to itself. Okay? Alright. But anyway, so now I just proved this one. Guess what? This was enough to say that these two triangles are congruent. Look, side, angle, side. Side, angle, side. But now, that's not what I'm supposed to prove. I already proved the triangle's congruent, but I'm supposed to prove that CD is congruent to CB. That this is congruent to this one. Well, guess what? Once you have proven triangles congruent, then you could say whatever you want about the triangles. If these two triangles are congruent, then all sides must be congruent. So you say that this is congruent to this one. So you write statement number 3. Okay? CD is congruent to CB. Segment, segment. Now, number 3. The reason behind it, well, congruent parts of congruent triangles are congruent, or as I call it, sipikitac. All right? Yeah, I know, sounds weird, but that's how you do it. All right then. So let's get cooking right here. So just a quick summary. Okay, I just want to go through a quick summary. So we have in center, all right here. The in center of a triangle, and let me zoom in a little bit. See, can I? Yes. Okay. The in center is located at the intersection of the angle bisectors. So in center goes with angle bisectors. Not only that, in center means that you could draw a circle inside. Okay. Circumcenter, okay, is located at the intersection of the perpendicular bisectors. So in center has to do with angle bisectors, and circumcenter has to do with perpendicular bisectors. So in is angle, circum is perpendicular. Okay, let's go here. The centroid. The centroid is the intersection of the medians. Now, why is this important? Oh, is it? When we looked at the construction part, when we're doing the construction, we were constructing the medians, we realized that this part right here, and let me zoom in, okay, forget about the definition right here. Let me zoom in, okay, right here. We noticed that this part right here, the one that goes from the vertex to the intersection, is twice as long as the other part of the segment. This right here is twice as long as this part. Got it? Good. And remember, centroid has to do with the medians. Okay, the next one then. The orthocenter. The orthocenter has to do with the altitudes. Alright? The orthocenter, look, located at the intersection of the altitudes of the triangle. In the case of the equilateral triangle, all 4 of the above centers, okay, occur at the same point. Only in the equilateral triangle. Alright, just remember that. So now let's get cooking. Alright. So let's start with this one right here. Okay, this is the guided practice. This is page number 9. So let's see. It says, in the diagram of triangle ABC and triangle DEF below, okay, AB is congruent to DE. So guess what? The first thing we gotta do is mark those things, okay? Because that's gonna give us the clues as to how to prove this triangle is congruent. So AB is congruent to DE. AB is congruent to DE. See that? Angle A is congruent to angle D. Angle A is congruent to angle D. Ah, you thought, right? You thought that A was going to go with F. No, not at all. But now we have the orientation of the triangles. Now we know that these triangles should be like, if we rotate it a little bit to the counterclockwise, we'll see that it looks exactly like this one. All right. So then, which method can be used to prove triangle ABC? Oh, wait. More information. And angle B is congruent to angle E. Oh, right there. What do you think? What method can be used to prove the two triangles congruent? Well, side, 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 side. I don't think so. Side, angle, side, side, angle, side, side, angle, side. No, I don't think so. Angle, side, angle, angle, side, angle, angle, side, angle. Oh my God, we hit the jackpot. So this is the answer. See that? It wasn't that bad, right? All right then. So now let's move on to the next problem. Right here. So it says the diagonal ABC, diagonal AC. Oh my God, I'm making so many mistakes. The diagonal AC is drawn in parallelogram ABCD. Okay. Which method cannot be used to prove that ABC is congruent to, triangle ABC is congruent to triangle CDA? Okay, I can tell you right now, you cannot use this method, and you cannot use this method. Okay, so that's it. We know this is congruent to itself, but anyway, so these methods cannot be used. Good, let's move on to the next problem. Okay. It says in the diagram below of triangle H, okay, H, and triangle old, all right, angle GAE, angle GAE, okay, right here, is congruent to angle LOD. All right, so what's up? To prove that these two triangles are congruent, okay, by side angle side, what other information is needed? Well, I need to prove that they are congruent by side angle side. Well, guess what? Do you see that these sides are already congruent? So if I make this a side congruent to this one, this will not be side angle side. It will just be angle side side. I need side angle side. Okay, so side angle side, like that, because the angle has to be in between. So side angle side. So I need, oh, okay. So the answer is AG congruent to OL. AG congruent to OL, and we just proved the triangles congruent. Let's move on then. Here, in the diagram of quadrilateral ABC, AB is parallel to CD. All right. So that doesn't tell me much, but anyway. So angle ABC is congruent to angle CDA. Angle ABC, ABC. So this angle is congruent to this angle. Okay, CDA, CDA. And diagonal AC is drawn. Which method can be used to prove that triangle ABC is congruent to triangle CDA? That this triangle is congruent to this triangle? Oh, sure. All right. So, guess what? This is a quadrilateral. Okay, I know that this side is congruent to itself by the reflexive property. Aha. What else do I know? Let me see. AB is parallel to CD. Oh my God, I get it. AB, this is parallel to CD. That makes this a parallelogram. And if I remember, opposite sides in a parallelogram are congruent. So this is congruent to this one right here. Ah, nice. And by deductive reasoning, this is congruent to this. Made a mistake. Just because two sides are parallel doesn't mean that they are congruent. And I'm going to show you what I mean. In the trapezoid, opposite sides are congruent, but parallel, but that doesn't mean that they are congruent. But now I know something. If this is parallel to this, I can basically extend this part right here. Okay? And I can extend this side right here. And I can do the same thing for these ones. Okay? So this is a transversal, right? If this is a transversal, then this angle is congruent to this angle because of alternate interior angles. All right. And what else? Nothing. That's it. Remember, you have angle, angle, side, angle, angle, side. Oh my God, I did it. So the answer is number 1. But Becker, how am I gonna know when they give me the question on the test? Listen, there is the only way to know is by exploration. You have to analyze the problem, just like I did right now. I assumed that because they were parallel, it was a parallelogram, and then I actually, retracted. I backtracked from that because parallel sides doesn't make a parallelogram. If they had said 2 pairs of opposite sides, then I could have said, okay, yeah, it's a parallelogram, and I know that opposite sides are congruent. All right, let's move on. As shown in diagram below. All right, so AC bisects BAD. AC bisects BAD. BAD. Okay, so this is an angle bisector, so this angle is congruent to this angle right here. Okay, what else? Angle B is congruent to angle D. Angle B is congruent. Angle B is congruent to angle D. All right. Woo. So I have angle, but now how can I prove a side congruent to itself? Oh my God, look, AC is congruent to itself by the reflexive property. So I have angle, angle, side, angle, angle, side. Okay, don't call this angle, side, angle, because it's not. It's angle, angle, side. So angle, angle, side, and we got this one. All right, let's move on to the next set of problems. All right. So, in the diagram of trapezoid ABCD, all right, below, diagonals AC and BD intersect at E. Okay, and triangle ABC is congruent to triangle DCB. All right. Which statement is true based on the given information? AC is congruent to BC. AC is congruent to BC. What? AC is congruent, to BC? Okay, first of all, a plane side? No way. Second one, CD is congruent to AD. CD is congruent to AD. CD is congruent to AD. I don't think so. Alright, the next one. Angle CDE, okay, is congruent to angle BAD, to angle BAD. Hell no, just by observation I know it's not. Alright, so let's try the fourth one. Angle, just because this is the last one remaining doesn't mean that I should not, this is the answer and I shouldn't go over it because I might have made a mistake. So angle CDB, angle CDB, this one right here, is congruent to angle BAC, BAC, congruent to this angle right here. Well, triangle ABC, this triangle right here, I'm gonna have to color code it with what? I have no idea. I need a color pencil. Where is one? Okay, I couldn't find a color pencil when I need one. Wow. Alright. So we're talking about ABC. A, B, C. This is the triangle we're talking about. Okay? So this is one triangle and this is the other triangle, just in case you're thinking that it's actually this one. No, it's this triangle right here and this triangle right here. So I know that if these two triangles are congruent, look, DCB, we're talking about this other triangle. Okay, So if that is the case, then this side is congruent to this side. This side right here, it's actually a common side. Okay? And what else? And this side is congruent to this side. This both sides congruent to this side. Okay. Therefore, everything else in these triangles is congruent. Okay? First of all, in this triangle, this is an obtuse angle. This is an obtuse angle. Alright? So, but that's not what they're talking about. They're talking about this angle right here, which is this angle right here. So then, that's why choice number 4 is the answer to our problems. It's tricky, and this topic is not just, you know, it's not like bread, like you just eat it. You have to think about it. Okay, it's not an easy task, but we can do this. All right, so we have the following. The diagram below shows a pair of congruent triangles with angle ADB congruent to angle CDB and angle ABD congruent to angle CBD. Yes, I just spoke a bunch of nonsense right now, but let's see which statement must be true. All right, so we got this angle is congruent to this angle, and this angle is congruent to this angle. How do I know the distinction? You see the two arcs right here? That means that this goes with this. Okay then. So, and this one is congruent to this. So out of all this, AD is congruent to CD, AD is congruent to CD. Well, I don't know. Let's see. BD is congruent to itself by the reflexive property. Okay. Now this, look at this. Let's talk about consecutive angles. B to A. Or not even. Let's see now. Yeah, let's go from E to A. Okay. So these triangles are congruent by angle, side, angle, angle, side, angle. So that means that this must be congruent. Okay, you see how long this is? Must be congruent to this one. Right? And that angle A is congruent to angle C. And not only that, that AB is congruent to BC. Right? And AD is congruent to CD. Oh, okay, so we found our answer. Man, this is crazy. But I guess we could do this. Alright, the next one. On the diagram below, and we have line or segment ABCD. AC is congruent to BD. AC, D is right here, is congruent to this right here. Okay? Now, using this information, it could be proven that BC is equal to AB. That BC is congruent to AB. No way. You cannot take some information at random in the middle without knowing what's going on. Let's see now. AD minus BC minus this equals CD. Wait. All these minus this is CD. That's not true, because you take away this part, but you still have this part and this part. So no. AB is congruent to CD. AB is congruent to CD. There's no way in the problem where it says that they are congruent. AB plus CD, AB plus CD equals AD. What? Now let me go over here. AB is equal to CD. AB is equal to CD, but how? Oh my God, I got it. AB, right? CD. Now let's give values. Okay, so this is the only way I'm gonna understand this. This is 4. Okay. This is AC is congruent to BD. That's all it says. AC is congruent to BD. So this is 3, right? Just for the sake of argument. So AC is 7, and it's supposed to be congruent to BD. I already have this as 3, so these gotta be 4. So like AC, which is 7, is congruent to BD, which is also 7. I mean, I just made it like that. If I subtract the 7 from this equation right here, what do I end up with? I end up with AB having the same length as CD. Oh my God. So the answer is number 2. You see? That's what I'm telling you. Like, don't try to cook the rabbit before you hunt it. I was already on choice number 4, and then I had to backtrack because I'm like, maybe I'm not sure about this. Alright, cool then. Let's move on to the next problem. Alright, when writing a geometric proof, which angle relationship could be used alone to justify that two angles are congruent? Okay, so if you have parallel lines right here, let's say parallel lines cut by a transversal, then you have to, you see, you already need the parallel lines and you need the transversal, and then you could say that these are ultimate interior angles. It doesn't work like that. But just by the fact, look at this choice, supplementary angles. No, it cannot be used just, okay, it cannot be used alone to justify that two angles are congruent. Supplementary angles, what are you gonna say? 70 is congruent to 110. No. Okay. Linear pair of angles is the same thing as supplementary angles, but together. This is a linear pair. If this is 110, this is 70, is 180, linear pair. Okay? Uh-oh, I need some water. Alright. Adjacent angles. These are adjacent angles as well. So no. What about vertical angles? Well, vertical angles are formed by intersecting lines. And basically, vertical angles are congruent. See that? Congruent. So the answer is number 4. Okay? Okay, now this problem. In triangle AED, okay, AED with segment ABCD, okay, shown in the diagram below, EB and EC are drawn. Okay, EB and EC are drawn. Now, if AB is congruent to CD, if AB is congruent to CD, okay, which statement could always be proven? Well, we have the 4 choices. Now, the first one says that AC is congruent to DB, that AC is congruent to DB. I'm pretty sure this is the right answer, but I need to prove it. Okay, so I'm gonna give values. AB is 4. This is just like one of the previous problems, I think, but backwards. So AB is 4, and it says that it's congruent to CD, so this one must also be 4. Okay, and I'm gonna give a value to BC, 3. Okay, so now let us look at the choices. AC is 7. 4 plus 3 is 7. DB is also 7. So this can be proven to be true. Now, how is that possible? Well, think of it this way. BC is its own side, okay, its own segment by the reflexive property. Okay, so BC is equal to BC. So if I add BC to AB and I also add it to DC, then I'm gonna end up with longer segments that are of the same length, and that's why. Alright, the next one. So given triangle ABC and triangle EDC, okay, C is the midpoint of BD and AE. I need to prove that AB is parallel to DE. Wow, this is gonna be a hard task, but let's see. So the first thing I do is I have to understand that this is the midpoint. So if this is the midpoint, okay, of BD and AE, that means that AC is congruent to CE, as well as BC congruent to CD, because the midpoint basically divides a segment into 2 equal parts. Now let us conduct the proof. Alright, so I'm gonna write my first statement. Let's see if I have enough space to write. So my first statement is gonna be the given. All right, you could write statements in one column. If you don't have enough space, I suggest you use a loose leaf paper, okay? So my first statement will be the following. C is the midpoint okay, of BD and AE. Okay, and how do I know that? Well, it was given to me, so it's given. All right, my second statement. Because I already saw that this was the midpoint, I can say the following. I can say that segment AC is congruent to segment EC, as well as, and, okay, I write and, segment BC is congruent, okay, to segment DC. Now the reason, why did I say that these segments were congruent? Because they told us that C was the midpoint. So you don't have to say because this is the midpoint, then the segments. No, all you have to write is definition of midpoint. Okay. Statement number 3. Remember that vertical angles are formed by intersecting lines, so I can say that this angle right here is congruent to this angle right here. Make sense? Okay then, so that's exactly what I'm gonna say. Now you cannot call this angle C because both of them will be angle C, so no, you cannot do that. You gotta call it by a 3-letter name. So I'm gonna say that angle ACB, okay, angle ACB, angle ACB is congruent, okay, to angle ECD. Okay? And why did I say that these two angles are congruent? Because they are vertical angles. Okay? And how do I know they're vertical angles? Because vertical angles are formed by two intersecting lines. So I'm just gonna say definition of vertical angles. Alright then, guess what? I just proved that this triangle right here is congruent to this triangle right here. Basically, in most of the proofs, triangles are involved. Now, these triangles are congruent by side, angle, side. Side, angle, side. So that's exactly what I'm gonna say. So triangle, okay, ABC is congruent to triangle EDC. EDC. Now they are congruent by side, angle, side. See? Starts to make sense how to write the proofs? Then I will explain to you how to write a different way of writing proofs. Alright, my statement number 5. What else can I say? I can say, okay, remember what I'm supposed to prove, that AB is parallel to DE. So I proved this triangle is congruent. Now notice something. These two lines, they say, okay, I need to prove that they parallel. I don't know. In order to prove that two lines are parallel, I need some type of like either exterior angles or interior angles. Since these two triangles are congruent, that means that every other part of the triangles is also congruent. So I'm gonna say that this right here, angle B, is congruent to angle D. Okay, I'm gonna say that angle B is congruent to angle D. And it is true. If you extend this side, okay, remember what I said, it's always valid to extend the sides. Then you end up with a pair of parallel lines. And if we look at this right here, and this is a transversal. So if we look at this angle right here, being congruent to this angle right here, because anyway, the two triangles are already congruent. So these angles must be congruent. But by looking at it like that, okay, we know that angle CDE is congruent to angle CBA. Okay, now why are they congruent if I already proved that two triangles congruent? Exactly. If once you prove that two triangles are congruent, then every other part of the triangles will be congruent to every other part of the other triangle. So we're gonna say that congruent parts of congruent triangles are congruent or reciprocal. All right then. Statement number 6. So we already know that these two angles are congruent. And notice this line right here acts as a transversal. So we can say that BD is a transversal. Okay? It's a transversal. Therefore, AB is parallel to DE. But how? Well, hello, we just said that these two angles are congruent. And if we extend these sides, we realize that these are nothing more than alternate interior angles. You see, one here and one here in the interior of the parallel lines. Okay, or in the interior of the lines. But the thing is that if two angles in the interior of two lines cut by a transversal are congruent, then the lines are parallel. This is one of the criteria that make the lines parallel. So therefore, my justification will be alternate interior angles. And that, my friends, conclude the proof for this problem. So copy it down so we can move on to the other problem. By the way, I hate these proofs, and I know you do too. But if you have this exploratory, adventurous spirit, then you'll find that this is quite entertaining. My hand hurts anyway, so let's move on to the next problem. Okay, here is a big problem. So, given AD bisects BC, AD bisects BC. So if this line bisects this one, that means that BE is congruent to CE. AB is perpendicular to BC. AB is perpendicular to BC. Therefore, this is a right angle. DC is perpendicular to BC. DC, where the hell is DC? Oh, DC is perpendicular to BC. So therefore, this is a right angle. Okay. They want me to prove that AB is congruent to DC. Not a problem. I'll do that. So I am going to work on the problem on the space. You see, I left some space right here. But if you don't want to, you could use loose leaf, okay? So I'm gonna start right here. So the statements, okay? And I'm gonna put the reasons right here. So my first statement, what is it gonna be? Easy. the givens. So AD, okay, AD bisects BC at E. Okay. I could end if I want to, and, or you know what? I could write the whole thing as one statement, or I could just write it as a different statement. AB is perpendicular to BC. And you know what? Here I'm gonna write it as one. But and DC is perpendicular to BC. Here he comes again. Anyway, I'm gonna continue working. So I am going to divide the columns, okay, because then otherwise I won't have space. Okay, so I made the division, so the statements and the reasons. So my first reason was given. My second reason was given. All right, good. Now let us go back up here. What else do I know? Well, let's see. Because of the first given reason, okay, I can say that angle B and angle C are right angles. So angle B and C are right angles. Okay? I'm gonna put it like that. I mean, if you want to, you could just write they are right angles. Alright, so my reason for that, well, how did they become right angles? How did they become right angles? Easy. They told me that AB was perpendicular to BC and that DC was perpendicular. So therefore, they are right angles because of the definition of perpendicular lines, or segments if you want to. All right. What else? Number 4. Any other conclusion that I can make? Of course I can. I can say that this angle is congruent to this angle because they are vertical angles. Okay? So I'm gonna say angle ACB, angle A. Sorry. I'm gonna say that angle B. Oh my God, you're right. Okay, sorry. These are vertical angles, but I'm not done with the right angles. So B and C are right angles because of the definition of perpendicular lines. Then after, in every statement, after you say that they are right angles, then you could say that angle B is congruent to angle C. Haha. Yes, right? Now, why are they congruent? Easy. All right angles are congruent. And that has to be true because they all measure 90 degrees, so they're all congruent. But what I'm trying to make you understand is that after you say that two angles are right angles, the statement that follows is that they are congruent, always. Okay? Because if you don't do that and you go on to something else, like I was going with the vertical angles, you forget about it, and then you won't be able to prove them congruent. Okay, so now my fifth statement. And now I'm going to go over to the vertical angles. So I am going to say that angle AEB. Okay, angle AEB. In other words, this angle right here. So angle AEB, okay, is congruent to angle DEC. Okay, DEC. This angle and these angles are congruent. Okay, I think I have enough proof to say that these two triangles are congruent. So I'm gonna go right ahead and do that. Remember, that's not what I'm proving, but in order to prove, you see what I'm trying to prove is that AB is congruent to DC. But in order to do this, and I see that I have two triangles, then I have to make sure that I have enough information. So I'm gonna say that triangle, okay, after you know that you prove them together, prove them congruent, then you're gonna say that triangle ABE, okay, is congruent to triangle DCE. The reason behind it, okay, did I miss something? Let me see. No, I didn't. The reason behind it, well, how did I prove them congruent? Angle, side angle, angle, side angle. Okay, so they are congruent by angle, side angle. So angle, side angle. See that? Okay then. And now watch this. I proved them congruent already. So to prove AB congruent to DC, to prove AB congruent to DC. Of course they are congruent. I mean, once you prove the two triangles congruent, then everything else is congruent for one reason. So I'm gonna say it. So I have proven that AB is congruent to DC, and the reason is that congruent parts of congruent triangles are congruent. All right, that's it. All right then, so let's move on to the next page. Yeah, I know this is not over yet. Don't worry, if you need help, I'm here to explain again. Alright, so in this part, they're gonna give us a couple of drawings, diagrams, and we're supposed to draw conclusions. So here, for example, they said that AC is congruent to CB. AC is congruent to CB. So what is my conclusion? My conclusion is that after they say that the segments are congruent, then you could always say that AC, see the measure of AC. Notice that I didn't put the bar on top. The measure of AC is equal to the measure of CB. And what is my reason? Definition of congruent segments. All right, so I'm not gonna talk that much. I'm just gonna do. I am gonna talk. BD is a median. Okay, so what is my conclusion? Medians go through from one vertex to the midpoint. So I can say that D is the midpoint of segment AC. Okay. Why? Well, because of the definition of medians. Gosh, somebody's having fun over there. Well, at least it's bothering somebody, not me. Okay, next over here. CD is perpendicular to AB. Okay, so what can I conclude? If this is perpendicular, I can say that angle ADC is right angle. Or I could say that CDB is a a right angle. I'm just gonna go like this, a right angle. Why? Perpendicular, so because of definition, okay? You on the regions or on the test, you have to write the whole thing. You cannot just write because of def. No, because of definition of perpendicular lines. All right, next. So BD bisects a angle ABC. BD bisects the angle ABC. This angle gets bisected. So I already know what my conclusion is. Angle ABD is congruent to angle DBC. Okay, ABD, okay, and the other one is DBC. They are congruent. Alright, and why? Because of the definition of angle bisector. Alright. Given two intersecting segments, conclusion. Come on. Intersecting lines form vertical angles. So angle 1 is congruent to angle 2, or angle 3 is congruent to angle 4. Just make one conclusion, okay? So angle 1 congruent to angle 2, or angle 3 is congruent to angle 4. And why? Hello, definition of vertical angles. Or if you want to say, you could say vertical angles are congruent, or if two lines intersect, then the angles, okay, the angles form, okay, no, sorry, if two lines intersect, they form vertical angles, and we already know which ones they are. All right, anything else? Let me see. Gosh, is this lesson ever gonna end? No, it's not gonna end, but you know what? This is a good thing to learn. Once you master this, once you make sense of this, you'll be able to prove anything. All right, so triangle ABC is isosceles with base AC. So what can I conclude? Well, I can conclude that side AB is congruent to side BC. So yeah, side AB is congruent to side, or segment AB is congruent to segment BC. Or I could also say that base angles are congruent if it's isosceles, because the base is AC. And now why? Well, two sides are congruent based on the definition of isosceles triangle. All right. Okay. The next one. So angle 1 is complementary to angle 2. So if they're complementary, I can say that angle 1 plus angle 2 equals 90 degrees, because that's what complementary angles are. And your justification, hello, just gotta say definition of complementary angles. Okay, the next one. So BD bisects AC. BD bisects AC. What can I conclude? Remember, we're not talking about angles. It says that BD bisects the segment AC. But what can I conclude? And this time I'm gonna give you time to answer. Right, exactly. I can conclude that D is the midpoint of AC. Segment AC. Y, definition of bisector of a segment. Funny thing is that some of you were thinking, okay, so if BD bisects AC, then this is the midpoint, so therefore AD is congruent to DC or CD, whatever you want to call it, right? No, you gotta go in order. If this is the bisector, then you have to state that D is the midpoint. Then if they ask you what else can you conclude, then you could say, oh yeah, that AD is congruent to DC. You understand what I'm saying? Okay. So now, the next one. E is the midpoint of AB. E is the midpoint of AB. Conclusion. Here they are already telling you that this is the midpoint. You understand? Here they were not telling you. They were just telling you that it bisects. Here they're telling you it's already the midpoint. So because it's already the midpoint, then you could go on to the next assumption. And you could say that, you see well, that segments, okay, AE, segments AE, all right, is congruent to segment EB. And that's as much as I can conclude. Now, why? Because of the definition, okay, of midpoint. Notice that here they were just telling me it bisects. So I have to write T is the midpoint, okay? And look at the definition of bisector of a segment. Okay? They did not tell me that this was the midpoint. I concluded that it was the midpoint because it was a bisector. Here, I concluded that these two segments were congruent because they told me that this was the midpoint. So I am using the definition of midpoint. Okay, you have to be clear when you state something. All right, given diagonal AC bisects diagonal BD. Okay, they bisect each other. So what can be my conclusion? If they bisect each other, where do they bisect? They bisect at the midpoint. So E is the midpoint, okay, of segments BD, okay. Remember, AC bisects this diagonal. It doesn't say that both of them bisect each other. This AC bisects this diagonal at the midpoint. Well, at E. Therefore, E becomes the midpoint of the diagonal being bisected. In other words, BD is the one that is bisected. Got it? Okay, now, what would be the reason? Well, remember, you're not going to say because of the definition of midpoint. No. We were talking about a bisector. So then, definition of, you could say bisector of a segment or segment bisector. See that? All right, cool then. Let's move on to our next task. All right, here you have a little gift from me to you. That's the quiz. So I'm gonna help you see what's going on here. Is it possible to locate the in-center of every triangle? All right, yes. Now, the next problem. We have a triangle right here. It says, how far is the centroid from the orthocenter? Okay, the centroid from the orthocenter. So, you tell me. You have choices right here, 4 units, 8 units, 16 units. So, which one? Well, first of all, let's recap. Remember what the centroid is. The centroid is formed by the medians, and the orthocenter is is where all the altitudes intersect. So I'm gonna say something right now. It is 16 units. And why is it 16 units? Well, memorize this. The centroid is twice as close to the circumcenter as the orthocenter. So if this is the, okay, let me see if I can zoom in so you could actually see it. Where is that remote? Okay, so we could see it now, and I could see it too. All right, so the circumcenter is 8 units from the centroid. Okay. Now, the orthocenter. Just look how far the orthocenter is from the centroid. Okay. So, the centroid is right here. If from the centroid to the circumcenter is 8, then from the centroid to the orthocenter is twice the distance. So then this must be 16. Okay? Got it? Alright, let's move on to the next problem then. Just remember this because it might be on the regions. So, I'm looking at a triangle where the orthocenter, the centroid, and the circumcenter all intersect at the same point. What type of triangle this is? Okay, which one is your choice?
Dad.
What happened?
Can you take a picture of it?
No, because I'm recording right now. Okay, now let's move on to our next problem. In rhombus ABCD, okay, the diagonals AC and BD intersect at E. Wait, hold on a second. If AE is 5 and BE is 12, what is the length of AB? Okay, so right now you could just go back to the previous lessons, okay, and come up with the answer. You know what? I'm gonna help you. I'm just gonna draw a rhombus. If you cannot draw it like this, then use a ruler. Alright, so the rhombus is A, B, C, D. Diagonal AC and BD intersect. So these diagonals intersect. Okay. AE is, where is, oh, they all intersect at E, okay. Like that, right? Okay. So, AE is 5. This is 5. BE is 12. BE is 12, so this is 12 right here. Okay. What is the length of AB? They want AB. Alright, so guess what? I know that the diagonals in a rhombus are perpendicular. So this is a right triangle. This is the right angle, so this becomes the hypotenuse. Okay? So we know that the Pythagorean theorem says that c squared equals to a squared plus b squared. So this is the hypotenuse, so x squared equals to 5 squared plus 12 squared. So x squared equals to 25 plus 144. Okay, x squared equals to 169. Then I have x squared, so I need to take the square root of this. At the end of every Pythagorean theorem, I take the square root. So what is the square root of 169? Beats me, right? So don't worry, I got you. Square root of 169 is 7 times 7 is 49, 3 times 3 is 9, okay, 13. Alright. So here, once again, let me see. The diagonals of a quadrilateral are congruent but do not bisect each other. The quadrilateral is, well, you need to think about it, okay? Number 6. Given three distinct quadrilaterals, a square, a rectangle, and a rhombus, which quadrilaterals must have perpendicular diagonals? Well, the rhombus and the square. Okay, and that concludes this lesson. My God, this long lesson. So I'll see you on the next lesson, okay? I just said lesson a bunch of times.